One of the most complex things to understand in fire is that when it comes to a beam column member heated up, the strains in the member get very complex very fast. At ambient temperature, strain's actually not that difficult to understand. You pull on a member and it gets longer. But now at elevated temperatures, when you've got multiple things acting together and temperature gradients across sections, stress and strain and understanding cross-sectional stress and strain can be one of the most complicated things. I remember in a lot of my PhD work trying to go through that, and you get results, and sometimes you even think these results are wrong. You go through the maths and see, no, this is actually correct. And you've really got to wrap your head around how this member is behaving. We're going to do a very sort of simple example now, but just to try illustrate how these concepts work together. For instance, here we've got a cantilever beam, and the normal structural mechanics, we add a load and our beam will get longer. So this we'd normally call mechanical strain. So it is our mechanical strain times by the length of the beam, where this is our original length of the beam. So that's the first strain we deal with. But now our building, this could be tension or compression, our column beam is standing there and it's exposed to a fire. So now you have some temperature, fire all around it, and we're going to assume this is uniformly heated. So it's nice, uniform all the way around. Now our beam's going to get longer once again. And this will then be the next component of strain. However, we have to be very careful when it comes to considering this. Normally with structural design, we'll call this a thermal strain, and then we times it by a length to get how long it elongates. But in reality, normally what we have is, we actually have four components of strain, where our total strain is the sum of our mechanical strain, our thermal strain, a transient strain, and a creep strain. All four of those occur. But the last two are actually quite difficult to quantify in fire. There are ways and means of doing it, but it is more difficult, because a transient strain, especially in concrete, is for heating on the first time, where it elongates. And then creep strain is a time-dependent phenomena, where it's heated, and as you apply the load, well, as the load stays there, over a period of time, the member gets longer. And these are quite difficult to model. So normally what happens, we actually exclude them. And all these last three terms kind of get lumped together, especially in your Eurocode models and your other models. They're sort of implicitly dealt with in the factors we use, and they all end up being lumped together in this thermal strain. So normally, as part of this course, we're going to deal with a mechanical strain and a thermal strain, but just to remember that of all of these, we do actually have a lot more happening in the background. For a simple beam, this is relatively easy to now deal with. We can actually see how it develops. But as part of the course, when we start considering a more complex profile, we have our beam once again. There's our cross-section. But now if we heat up the bottom part of it, what will happen is you've got part of the beam which is experiencing a thermal strain and part of the beam that is not. And the beam's going to actually try curl upwards. And you can end up with extremely complex mechanical strains in the section that may even look like something like that, which is initially counterintuitive and may even seem wrong. But those are the sort of things we may end up when going through all the calculations. But this is just to give an idea of the different strains. Remember, once again, total beam, apply a force, it gets longer, apply a temperature, apply fire, and it gets longer once again, and we end up with a total strain. But once again, this is also the case where we need to consider what happens when there's restraint. Because now we can have a time where the total strain is zero. If the total strain comes zero, this is now between a rigid concrete structure each side. It's in the middle of our building, there's a lift shaft one side and a stairwell the other, and the beam heats up and it can't go anywhere. Our total strain will suddenly become zero, which then ends up that our mechanical strain just equals the inverse of our thermal strain. And at that point in time, when the total strain is zero, where the beam has nowhere to go, that's when we introduce huge forces into our members. Because as it heats up, it's held in place, and the member then can experience large compression. And actually, that is often what can cause the building to fall down and fail, rather than necessarily the fact that it's 700 degrees Celsius and the steel's at 30% of its original strength. It's rather the forces we induce. And even this concept is applied in our beam in our cross-section, because what happens there, even though the beam may be free to expand, the cross-section, part of the cross-section restrains the other. This one's trying to expand where it's heated up, where this one does not want to expand. So part of it gets put into tension, part of it gets put into compression, and as it expands, it also tries to rotate, so you introduce a moment into the whole section. So the strains that then result can end up, as I said, very complex stress patterns. And just keep that at the back of your mind when you're doing your calculations. We, as part of this course, will normally consider fairly simple designs and analyses, but the real final results may be actually a lot more complicated than our calcs are leading us to think. Thank you.